Hey there guys, welcome to Unit 7 Note C, the last of our gas laws. We're going to look at stoichiometry in terms of gases, and then we're going to look at two new gas laws, Dalton's Law and Graham's Law. So first let's start with stoichiometry for reactions that have to do with gases. We can still use those balanced equations in order to come up with mole ratios, but we can also look at the role volume will play. So let's look at an example. Here we have hydrogen peroxide in a reaction where it breaks down into oxygen gas and water. Notice the mole ratios here. We have 2 moles of hydrogen peroxide, 1 mole of oxygen, and 2 moles of water. Since it said it's stoichiometry, we know that that's going to be an important factor, right? Let's look at the actual information given in the question. Hydrogen peroxide used for bleaching hair. Great, who cares? What mass of hydrogen peroxide? So I found the what and what I'm looking for. So I'm trying to find a mass or an amount of hydrogen peroxide. Must be used to produce 1 liter of oxygen gas at 25 degrees Celsius and 1 atm. Now that's starting to look more like gas laws, right? It's giving me liters, degrees Celsius, and atm. So let's jot that down. 1.00 liter would measure volume, whereas 25 degrees Celsius would measure temperature, and then I have 1 atm, and we know atmospheres is a unit for pressure. So we have 1 volume, temperature, and pressure. Since I'm only given 1 of each, I know it's going to have to be the ideal gas law and not one of our other comparison laws. So we've got R involved for the ideal gas law, and since that's 4 given numbers, I can then solve for the 5th variable, which would be moles. So once I know I have enough to make some progress, let's go ahead and solve for that, and then we can figure out what that can be used for. So we're going to go ahead and write down PV equals nRT. So the pressure was given to be 1 atm. The volume to be 1 liter. The moles was the question mark, or the thing that they didn't give us. We might not know why we need it now, but we know we can solve for it. And then the R is the big constant, 0.0821 liter atm over mole Kelvin. And then the temperature, instead of plugging in as 25 degrees Celsius, you always have to convert to Kelvin. So probably should have done this first. 25 plus 273 Kelvin is 278 Kelvin. And that's what I'll plug in to my ideal gas law. Not 278, 298. Wow. 298 Kelvin. Sorry about that. Standard temperature for thermo, actually. 298 Kelvin. I'm going to plug that in on the side. So what I can solve for now is my number of moles. Using 1 atm in 1 liter and dividing by the big gas constant and our temperature in Kelvin. What do we get for the number of moles of that substance? When we solve for n, we should get 0.0409 moles. Notice the 0.00 here and here, and then the temperature also having 3 significant figures when converted to Kelvin. We have moles as 3 significant figures, 0.0409. Now, what's the catch here? What did we really just solve for? We found the moles, and we're being asked for a mass. So typically, how do we go from moles to mass? We would use the molar mass. So if I started with 0.0409 moles, put that over 1, I could put mole on the bottom and gram up top. Always 1 mole. The question is, what molar mass would I use? So I'm trying to find the mass of hydrogen peroxide. Is this the moles of hydrogen peroxide? Wait a minute. It said this was all information for oxygen. So this would then be moles of oxygen. So if that's moles of oxygen, then I would need here the molar mass of oxygen, 16 twice, or 32.00 grams of O2. So how could I get to the mass of hydrogen peroxide? Well, I'm going to have to convert from one substance to another substance in a process known as stoichiometry, where you're going to use your mole ratios from your balanced equation. So we're going to go ahead and plug in our moles of O2 to our moles of H2O2 instead and use the molar mass of the H2O2. So I'm given mole to gram, but as H2O2, not as O2. Ah, shit. I fucked that up. Sorry, Mike. What did I just fucking do? I went from moles of O2 to grams of O2. Why would I do that? All right, at least it's at the beginning. Okay. All right. 1, 2, 3. Hey guys, welcome to Unit 7, Note C, our last set of notes on gas laws. We're going to go over gas stoichiometry today and then 2 new gas laws, Dalton's Law and Graham's Law. So first, let's look at the stoichiometry of gases. Stoichiometry, of course, having to do with the mole ratios, comparing 2 different substances. And then when we look at gases, we're going to focus on how volume plays a part in these calculations. So let's look at an example. Here we see the decomposition of hydrogen peroxide, where hydrogen peroxide breaks down into oxygen and water. In the question, we can see we're looking for the mass of the hydrogen peroxide. So I'm looking for mass of reactant. But let's look at what we're given to get there. We have 1 liter of oxygen gas at 25 degrees Celsius and 1 atm. So that's where I'm going to start my list of variables. 1.00 liters, 25 degrees Celsius, and 1.00 atm. So liters would be volume, degrees Celsius would be temperature, and atm would be pressure. Since I only have 1 of each, I know I'm not going to be using a combined or one of those other gas laws. It's going to be an ideal gas law question, so I know I'm going to need R. So R equals 0.0821 liter atm over mole Kelvin. So if I have these 4 things, what could I solve for next? N, or the number of moles. So how many moles do we have given these initial variables? The one thing that I want to check is units before we move forward. Liters, yes. Temperature in degrees Celsius, problem. So we're going to add 273 to be 298 Kelvin. Pressure in atm is good. All to match with R, so we can calculate moles. So here we are ready to plug in for the ideal gas law and solve for the number of moles. So we should get 0.0409 moles. We are using 3 sig figs. Notice the 0.00 on each of these. And then when you convert 25, adding 273, that becomes 3 significant figures for your temperature. So yes, 0.0409 moles. So how do we go from mole to mass? How do we go from mole to gram? Well, typically we've used the molar mass. How is this question different? It's giving you moles of one substance and asking you for the mass of another substance. Pay attention to the question. 1 liter of oxygen gas. So if this is all information about oxygen gas, then what did I really just solve for moles of? Well, of the oxygen gas, of course. So how could I convert from moles of oxygen gas then to the amount of the hydrogen peroxide? You're going to need your mole ratio. So let's start with what we're given. 0.0409. We're given for this step, I should say, what we just found. Moles of O2, which we'll go ahead and put on the denominator of the next conversion factor. Since I'm in moles, now I'm allowed to switch substances. So here's my opportunity to go from oxygen to hydrogen peroxide. So I'm going to stay in moles, but now I have H2O2. But I wanted mass, so we're going to add that one other conversion factor to go from moles on the bottom. We have moles up top, right? So we're going to put moles on the bottom of H2O2 and convert that to grams of H2O2. So now what numbers are we plugging in? Whenever you see mole to mole, you know you have your mole ratio. And so that's always going to come from the coefficients of the balanced equation. So for hydrogen peroxide, we have 2. And for oxygen, there's nothing, which we would read as a 1. Outside of your mole ratio, it's always 1 mole. And so now we just need the molar mass of H2O2, or 2 oxygens and 2 hydrogens. So 16 twice would be 32, plus another 1.01, so we're somewhere around 34 grams of the H2O2. So we can convert moles of oxygen to moles of hydrogen peroxide by multiplying by 2, and then if you multiply that by the molar mass, you get your final mass. So let's see what that is. Specifically, 2.78 grams of H2O2. So this is essentially combining 2 skills that we've learned already. We already went over the ideal gas law, and we've already gone over mole conversions. So now we're just putting those together in the same question, and that's what gas stoichiometry is all about. Using a gas law and then using stoichiometry to convert whatever you find moles of into whatever it's asking for of the other substance. All right, on to our next gas law. So we're going to start getting into something called Dalton's Law. Dalton's Law is all about partial pressures, or pressures of multiple pieces that are all in the same chamber, a mixture of gases. So the idea here is that in a mixture of gases, the total pressure is equal to the sum of the partial pressure. This is actually a very simple concept. If I have a balloon, and in that balloon I have 1 atm of helium gas and 1 atm of hydrogen gas, all together I have a total of 2 atms. The parts that are pressure, the helium and the hydrogen's part, add up to the total pressure of 2 atm. We can get the same concept if we look at just the moles. So if I have 1 mole of hydrogen gas and 1 mole of helium gas in that balloon, then I would have a total of 2 moles. So the idea of using moles instead of partial pressures is called a mole fraction. The catch is mole fraction is actually kind of a misnomer. It doesn't really mean fraction. So here's how I would do it for this example. I would take, let's say I want to find the mole fraction for the hydrogen, which would just be 1 part hydrogen divided by the 2 total moles in the whole balloon. So that would be a mole fraction of a half, right? Mole fractions are actually represented in decimals. So the mole fraction should actually be 0.5. If I added a 1/3 mole, let's say I also have a mole of oxygen gas in here, then I would be dividing by 3 total moles. And so my mole fraction would be 0.3. So it's just taking the part divided by the whole, but it's not a percentage. So you're not multiplying by 100. You just stop at the decimal version there. You don't leave it as a fraction. You don't take it all the way to a percentage. You leave it as a decimal. So that's our mole fraction. So let's try another example with some more numbers here. And let's try to think about sig figs as we go on this one. So now my theoretical balloon has 1 mole of helium, 3, I just said think about sig figs and then I didn't copy it down right. 1.0 moles helium, 3.0 moles neon, and 2.0 moles of argon. All 3 of those things exist in the same balloon, so the total moles in the balloon can be calculated by adding up the 3. 1 plus 3 plus 2 would be a total of 6.0 moles. Remember, your significant figures rule for addition is that you go by decimal places. So our answer is going to have this 1 decimal place. Keep that 0.0. Okay, so if that's my total moles, I could find the mole fraction by taking any one part and dividing it by that 6. So we're being asked to find it for neon. Neon's part was the 3 moles, 3.0. And I'm going to divide that by the total, 6.0. So 3 divided by 6 is again a half, but we're going to keep it as a decimal, so 0.5. But notice that each of these had 2 sig figs, so let's go 0.50. So 0.50 would be the correct mole fraction for neon in this example. So we're just doing parts of a whole, but not a percent. Partial pressure and mole fractions have a very close relationship. The idea is that you can sum each part up to get the total. So Dalton's law actually can be expressed by saying the pressure of the total system would be the pressure of the first part plus the second part plus the third part, and so on. So you could do this for 2 gases or 100 gases. The idea is just that you're adding up those percentages. Or I'm sorry, not percentages, those total pressures. So let's look at an example. This time I have 100 milliliters of gas at 25 degrees Celsius that has a pressure of 3 atm. Again, 100 milliliters, again 25 degrees Celsius, but now a pressure of 2 atmospheres. So what would be the pressure if I mixed those two things together? So think about this for a second. Volume's the same, temperature's the same. I'm being asked to come up with a pressure for a combination of gases. So all I really need here is Dalton's law. What would be the total pressure if part of it was 2 atmospheres, another part of it was 3 atmospheres, and then I put them together in the same container? I'm going to just sum those pressures, and so it would be 5 atm. It would be 0.00 because when you do addition, you keep the decimal places. So we've got 5.00 atm for our final answer. So they like to make these nice and wordy because actually the math is very simple. You're looking at a combination of gases, you just add the pressures. Now let's talk about vapor pressure. So this is where this addition of pressures can get a little bit tricky if we don't understand its application in a lab. So we did talk about this definition of vapor pressure back in chapter 1. The idea here is that you have a system, and it's a closed system, and you have both liquid water and water vapor, and it's the vapor or the gas pressure on the liquid of itself. And we've reached something called equilibrium, which we'll talk about in a future unit. The idea is that this is kind of a static closed system, and it's the gas pressure on its own liquid. That does change with temperature because as you increase the temperature, more and more of those particles would be in the gas phase. So you get more and more pressure pushing down. So you can see here with an increase of temperature, you get an increase of the vapor pressure. Vapor pressure is something that you could look up, something that there is a table for. So the idea is we can actually use this in a lab in order to help figure out a more precise answer to a question. So what happens is the questions typically ask about a gas being pumped into a system or something being collected over water. So let's take that same idea that I have liquid water here. If I have liquid water here, I also have water vapor above. So if I am collecting by displacement of water, if I am putting some kind of gas into the system, let's say hydrogen gas, and I want to then find how much hydrogen gas I have, the problem is that the pressure in this entire area would basically be contaminated by water. So I could basically write for this example that this total pressure, P total, would be equal to the pressure of that hydrogen gas and the pressure of the water. So if I'm interested in only the pressure of the gas, I can rewrite this as the pressure of the hydrogen gas is the total pressure minus the pressure of the water. So this typically happens by a reaction happening in the system with the water, and so then the gas is being created and the water is allowed to leave the system. So we can now collect this gas. We were just interested in removing the water pressure. The other thing that's going to make this easy is that I know that the total pressure would have to be equal to the atmospheric pressure on the outside. And there are actually some things that we can do in the lab environment to make sure that happens. So our atmospheric pressure could be considered the total pressure, which means it's something that we can just measure on the outside. And then we can subtract out the water pressure and get the pressure of the gas. And a lot of times they'll call this a dry gas because we've removed the water from it. So these are basically the generic versions of applying Dalton's law to this lab system. We can get the atmospheric pressure would be the total pressure of the gas and the water. So if we're interested in just the gas, you take the atmospheric pressure and subtract out the water. So there's actually a lab, a molar volume of a gas lab. That's a really big deal on the SAT, or the, subject test for chemistry on the SAT. So I'm going to do a separate video on just that experiment and some of the SAT type of questions that come up for that. Just a heads up if you want to check that out. All right, let's focus on the kind of questions we're going to see in this class. So first, we're going to collect some oxygen by displacement of water. Look at that wording. Collected by displacement of water. So that means that I have a system of water, and if it has liquid water, it's going to have vapor water. And then I'm also going to have oxygen gas. So this tells me I'm going to have this issue where I need to get rid of the water in order to isolate the pressure of the oxygen gas. So it tells me about that oxygen that I have 742 milliliters, which would be my volume. It tells me the temperature is 27 degrees Celsius. Degrees Celsius would be my temperature. And then it tells me the barometric pressure was 753. Barometric pressure, or atmospheric pressure, basically the same thing, would be the total outside pressure. So I'm going to be kind of careful about adding this to my list of things that I know are true for oxygen. What they're telling me is the total pressure. Pressure total is going to be 753 millimeters of mercury. What volume, so there's my what, I've got a V question mark, would the dry oxygen, so there's another hint there, dry oxygen meaning without water, would it occupy at STP? Now remember that STP is giving you numbers as well, the temperature of 273 and the pressure of 1 atm. So let's go ahead and write those up here too. Pressure 1 atm, temperature 273 Kelvin. So as a sample was collected, the oxygen occupied, it looks like I missed. We've got the volume, volume was given here. The question is asking what volume would it occupy at STP. The V question mark actually goes with this set. Sorry if that confused you. And the pressure that I'm missing here is this problem. So just to clarify, sorry about that. The volume and the temperature in the initial situation are the 742 milliliters and the 27 degrees Celsius, which you know you want to add 273 to because it's got to be in Kelvin. And then it gives you some information about pressure in this first situation, but the problem is that it's giving you a total pressure. You're going to have to fix the water problem. And then it gives you a second or final situation where it's asking for the volume at STP. So we're finding the V question mark for the STP combination. So this is starting to look like combined gas law over here pretty much, but we have the problem that we kind of have two unknowns at this point. We don't know the volume at STP, and we don't know the pressure in the initial situation. But we do know the total pressure, and then notice here in parentheses, it gave me the pressure of the water. So the idea here is if we subtract out the pressure of the water, we can get the pressure of that oxygen gas. So the pressure of the water is 26.74 millimeters of mercury. And so if we subtract their barometric or atmospheric pressure, subtract out the water pressure, we can get the oxygen pressure. That's going to then allow us to plug that number in for the first situation in the combined gas law. So I know my handwriting is getting a little messy here. Let me erase this and clean this up for you. So first thing is to isolate. When you see collected by displacement of water or dry oxygen, we want to figure out what the real pressure is. So we're going to take the barometric or atmospheric pressure and subtract the water pressure. So we get a new pressure of 726. Notice we're going to the least decimal, the ones place here. Then we want to use that pressure with the other variables given at that time. So the oxygen occupied 742 milliliters at this temperature while the barometric pressure was this 753. So we're going to adjust the 753 to be, where'd it go? 726 to plug in for the first pressure. Then your first volume is not in milliliters, but in liters. And then your second temperature would be your STP. Then we have the first pressure, which was your STP, the unknown volume, and then the first temperature, 27 degrees Celsius, changed to 300 Kelvin. So we're making sure that our units match. They don't have to be the same as R for combined gas law, but they do have to match. So since this was in millimeters of mercury, the 1 atm is changed into millimeters of mercury. The temperature has to be in Kelvin. And actually for the volume, you could have left it in milliliters or you can solve it in liters. Either way, the volume that you get in the end would be whatever you used. If it specified which one it wanted, you would want to make sure you changed it. But in this case, it really doesn't matter. So if you solve for this, the volume would be 0.645 liters or 745 milliliters would also be perfectly fine. So to recap this, we're using Dalton's law to adjust the pressure and then going back to our original gas laws, in this case, the combined gas law, and solving a problem that way. All right, let's take a quick break before we start Graham's law. We'll be right back. Welcome back. Let's get into Graham's law, our very last gas law. So Graham's law is going to help us determine effusion rates or rates of travel for gases. So let's think about this with some background information you already have. This would actually be a really good Graham's law question, and I bet you can answer it already. What do you think would travel faster, neon or xenon? Well, neon only has a molar mass of about 20 grams per mole, where xenon has a molar mass of over 130 grams per mole. So does that give you a hint? Remember the third postulate of kinetic molecular theory? Said that if I have an increased mass, the travel would be slower, the particle would move slower. So since neon has a much lighter molar mass, it would move much faster. And that's exactly what Graham's law is all about, the rate of the movement. But for gas laws, we're going to use something called effusion. Now, effusion is very similar to diffusion. Where diffusion, you may recognize the definition, moving from a high concentration to a low concentration. For example, putting a drop of food coloring in water, you can then watch it spread out. The high concentration of the color would diffuse into the areas where that particle was less concentrated. So high concentration to low concentration is diffusion. The only catch for effusion is that it's more controlled. Instead of expanding in a million different directions, it's actually only going through one particularly small hole. Picture taking a balloon, and you can put a piece of tape on it so it doesn't pop when this happens. You poke a small hole through it. You would be able to hold that up to your face and feel the air coming out. You can feel the air passing through a small hole, which is going to be much better for us to actually measure rate. So we call this Graham's law of effusion. So we can look at the rate at which particles move through a small hole. You can also see how particle size or mass would play a role in this. Bigger particles would have a harder time moving through the small hole. Okay, so here's the formula. The rate of the first substance compared to the rate of the second substance is equal to the square root of their molar masses, but inversed. Notice if I'm looking for the rate of rate 1 as it compares to 2, I put the molar mass of the second thing on top and the first thing on the bottom. This looks like one of our most confusing gas laws, but it's actually not so bad because we're typically solving for that rate ratio as one number. So we want usually a decimal, some kind of number here that will give me an idea of how the substances compare. So if I wanted, for example, the rate of oxygen gas compared to the rate of helium, I would get one number. Say it moves twice as fast. The number I would get here is 2. If it moves half as fast, the number I would get here is 0.5. So you're solving for this number as a whole by using the molar masses to get you that rate comparison. Just be careful that whatever you want the rate of as compared to something else, that molar mass goes to the bottom because the relationship between rate and molar mass is inversed. If I have a higher molar mass, it moves slower. So small things, small particles will have the fastest effusion rate. So we're looking for low molar mass to be the faster particle. So let's use hydrogen gas versus helium gas as an example. And remember that hydrogen is one of our diatomics. So we have H2 versus He. Which one will move faster? The H2 would move faster with a molar mass of 2.02 as opposed to helium's 4.00. So it would move faster. How much faster? So we're actually going to be able to use this rate ratio in order to calculate the exact number of how much faster. Is it 5 times as fast or 10 times as fast? Twice as fast? So I'm solving, remember, for this entire thing as a whole, so I'm not changing that. Rate of H2 as it compares to the rate of HE. Then I'm going to put the molar mass of HE on top, which was that 4.00. And then I'm going to put the molar mass of the H2 on the bottom, which was the 2.02. So calculating 4 divided by 2 and then finding that square root of that number is going to give me the ratio of how much faster hydrogen moves than helium. When you get your final answer, simplify it to the decimal point. Don't leave this as a fraction. Don't leave the radical on it. I'm not doing your math for you. Give it to me as a decimal. Plug it in the calculator. What is that decimal? We aren't going to go over significant figures with radicals, so I'm not going to be grading on significant figures for Graham's law. So roughly speaking, round somewhere reasonable, we get a rate of about 1.41. So that would mean that hydrogen moves 1.41 times faster than helium. We can also do this the other way around. Knowing that helium is slower, we can look at how much slower. If I wanted to look at this in respect to helium, I would let helium be the number 1, which means I would then put the molar mass of helium on the bottom. So let's see if this changes our number any. Again, I'm not changing anything on the left, so I've got rate of HE as compared to the rate of H2. So now I'm going to put the molar mass of the hydrogen on the top, the 2.02, and I'm going to put the molar mass of the helium on the bottom. So math-wise, you can already see, of course, we should be getting a different number. So if I find 2 divided by 4 and find the square root of that number, what do we get now? So we would get about 0.71. So this would be read that helium moves 0.71 times as fast as hydrogen. What do you think the relationship between the numbers 1.41 and 0.71 might be? How could these numbers be related to each other? They're actually inverses of each other. If you punch in the calculator 1 divided by 1.41, you're going to get 0.71 and vice versa. This is because if you're 5 times faster than me, I'm 1/5 as fast as you. These numbers are inverses of each other. You've just got to be careful what you put in the number 1 position, because that is what you're going to get your rate relative to. So you got to be careful what goes on top and how you translate that. The hydrogen is faster, so it'll have a number above 1, where the helium is slower, so it would have a number that is less than 1, 0.1 times as fast. So that's going to give you your ratio of how much faster or how much slower, and that will be our very last gas law on Graham's gas laws. All right, guys, that's going to wrap up the notes for Unit 7. Our next unit will be Unit 8, where we're going to talk about solutions. See you there.